Welcome to Introduction to Data Analysis. Today I'm going to cover a few introductory matters to how we think about statistics. There are many big issues in data analysis, excuse me, and what I'm going to talk about today, I guess, is a relatively intermediate level statistical explanation of some of these concepts. In particular, I want to talk about null hypothesis significance testing, power analysis, effect size, confidence intervals, accuracy and parameter estimation, and meta-analytic thinking. So, what is inferential statistics? What is it that we're trying to do with inferential statistics? When we do a statistical analysis, we're often concerned with getting estimates of population parameters. And we use our sample data, from which we get sample statistics, to estimate those population parameters. So take, for example, the population mean. There is this underlying data generating process, and it is assumed to have a certain mean. And then we use our sample data, which has a sample mean, and we use that sample mean to estimate the population mean. Of course, every time we sample our data, we will get a different sample mean. And we hope that that estimator of the population mean is a reasonable estimate of the population mean. Other times we might have population parameters such as the differences between two means, as in a two-group t-test. And we use the differences between the sample means to estimate the population difference between means. There are many different population parameters that we might be interested in, and the aim of statistics is often to get an estimate of that population parameter and also to quantify uncertainty about that population parameter. Other times, we want to do hypothesis testing. We want to say how likely is the data we have, how likely is the data to have arisen from a given hypothesis. So for example, if our null hypothesis is that there is no relationship between two variables, or there's no difference between two group means, that might be our null hypothesis, that the difference between two means is 0 in the population. And then we might have an alternative hypothesis that those two means do differ in the population, that the two means are not equal. And the traditional approach to statistical inference used in psychology is to start with the null hypothesis and then see whether the data provides sufficient evidence to reject that null hypothesis. And that's where test statistics come into play, such as t-statistic or chi-square statistic or an F-ratio statistic. And we get a value for that statistic, and that value is related to some distribution. And we can see the probability of getting a value that large if the null hypothesis were true. And if the probability of getting such a test statistic value that large is very unlikely, then we say that perhaps the model, the null hypothesis, it would only generate such data in very rare settings, very rare occasions. Therefore, perhaps we should reject the null hypothesis and accept the alternative hypothesis. So this is an approach to statistical inference that we often take for granted. And of course, that raises the question about what level of unusualness is required in the data. How different, how unlikely does the data need to be given a model for us to reject that model? And that's what we define as alpha. Typically alpha is 0.05, but it could be 0.01. And that's saying that if the data, this extreme or more extreme, would only arise 5% of the time, 1% of the time, whatever alpha is, if it's less than that, if it's less than alpha, then we should reject the null hypothesis. This is a traditional approach to inferential statistics. Now, over time, statistical procedures become standardized, and there is a tendency, and I think particularly in fields like psychology, where not everyone is focused on statistics. Not everyone is focused on understanding all the details of statistical analysis. A lot of researchers are more concerned about substantive matters. The mathematical background of many researchers may not be as strong. There are many other concerns of researchers. So there's often a tendency in applied fields that use statistics to develop conventions and standardization around how to interpret statistics, and often they're not the best approaches. One particularly undesirable thing that has evolved over time is a sort of excessive focus on p-values. A conflation that a significant p-value indicates an important effect. And so you'll see some people interpreting, saying, well, look, my p-value is significant, therefore the effect is interesting. Or the p-value is not significant, therefore there's nothing there, which is a further problem of, yeah. So what I'm hoping to talk about is a few interrelated topics which discourages you from just merely focusing on p-values, but thinking about things like effect size, power analysis, and confidence intervals, which provides us with a much richer language for designing our studies and interpreting the results. And hopefully, we can weave this together into an overall picture of how to do data analysis. I should also flag at this point that this is still all ground in what we can call frequentist statistical methods. There is another approach called Bayesian statistical methods, which provides another lens and another perspective on many of these issues. And there are correlates to concepts like confidence intervals, and certainly power and inference can still be applied there. And in some ways, some might argue that the statistical framework of Bayesian statistics is superior to the frequentist one in terms of the inferences that we can naturally make. But for this course, we'll be focusing on frequentist methods, which are far and away the dominant approach traditionally in psychology, albeit that Bayesian methods are becoming infrequently more popular. So first, let's talk about what is an effect size. What are we trying to do when we do research? Well, typically we're trying to refine our estimates of population parameters. And often the parameters of particular interest are what we might describe as effects. There are many examples in psychology. Common ones might be the correlation coefficient. So the degree to which two variables are linearly related, and it also incorporates the direction of that relationship. Cohens D is the standardized mean difference between standardized difference between two group means. But there are also unstandardized measure of effects. So the Cohens D and Pearson's are our standardized measures of effects. But there are unstandardized measures of effects. So we could look at just the raw group mean differences or a regression coefficient. All these quantities capture something about the relationship between two variables. And ultimately, when we're trying to explain the importance of an effect, it is these quantities which we wish to look at. So, for example, if we're trying to describe the effect of a drug, the effect of taking a drug on, say, performance, arousal, and so on, we may want to quantify that relative to the control group and describe whether it's a big or a small or a medium effect based on our understanding of the dependent variable and the context and so on. Now, the important point is that effect size is what we're interested in. Statistical significance does not mean that we have a large effect. Just because the p is less than 0.5 does not mean we have a large effect size. As we will soon see, statistical significance depends on several other factors, most notably sample size and our alpha. And so the important point is that we're trying to understand effect sizes in our research, and we're trying to interpret those effect sizes appropriately relative to our estimates of population effect sizes. Now here's a big table, and it aims to just flag just how many things there are out there that we might describe as effect sizes. And these are sort of common effect sizes that you might encounter in psychological research. You know, we've got a number of effect sizes that look at group mean differences. There's others that are more look at more variance explained, in terms of percentage of variance explained in a regression or in a analysis of variance context. Others are sort of ratios of one variance to another. Some of them are standardized, some of them are not. One thing that you first need to determine when you're dealing with effect sizes is how to interpret them in a language that is sort of meaningful to your research context. And you know, Cohen proposed some rules of thumb reluctantly to give language to what effect sizes mean. And so, for example, often a Cohens D of, say, 0.1 or 0.2 might be considered small, 0.5 might be considered medium, 0.8 might be considered large. And there's similar sort of rules of thumb for correlations. We shouldn't take these rules of thumb too seriously. It's important to build up an intuition as you read research to start to see effect sizes contextualized relative to the literature, relative to other effects. So if you're, for example, reading literature on training and looking at the difference between trained and not trained, or benefits pre-post in terms of performance, you might compare interventions in terms of the sizes of effects the different training programs can achieve. And you can start to think about the cost benefits of, say, more elaborate training versus shorter training, and the types of performance improvement that you might see. And so these rules of thumb are just one way of thinking about starting points for getting a language for talking about effect sizes. This slide aims to show the connections between power analysis, effect size, and statistical significance. Three very important ideas. First point is population effect size is not affected by your sample size or your alpha. It's some truth, we assume. If you take a frequentist perspective, we assume that there is this effect that is true in the population. There is a data generating process, and we are sampling from that effect. So the aim of this effect size is to understand the degree of relationship or the size of effect in the population or in the data generating process, whatever that true effect is. Power is the probability of finding a significant effect, assuming conditional on there being a given effect in the population. So it is a function of your sample size, population effect size, and alpha. Specifically, if our sample size gets larger, our power should increase. As population effect size gets larger, our power should increase. And as alpha gets smaller, like goes from 0.5 to 0.01, our power should actually reduce. Hopefully this makes sense. The bigger the sample size, the more precision our knowledge will be, and the more we'll be able to determine whether something's a real effect versus possibly coming from just some random process. Likewise, the larger the effect there is, the easier it will be to find that effect. Whereas subtle effects, it's harder to detect. And alpha is kind of our decision threshold in terms of how much deviation from, say, the null hypothesis do we need to see to rule out the null hypothesis. So the smaller that p-value, we're saying we need more and more evidence. Finally, statistical significance, i.e. our p-value, the degree to which our p-value is small, is a function of our power, which we saw as a function of other things, and some random processes. So if we have a lot of power, then we would expect to see a statistically significant p-value or test statistic. But just by random sampling, that p-value is going to vary, and sometimes, unless you have 100% power, you're going to see non-significant effects, even though there is this population effect to be discovered. So we can contrast a focus on effect sizes versus a focus on null hypothesis significance testing. So null hypothesis significance testing is asking the question about what's the probability of obtaining the study's results if the null hypothesis were true, i.e. the null hypothesis being no difference between groups, no relationship between two variables, and so on. So the aim is to first, if we're going to answer that question, we work out an appropriate significance test. Hopefully that's meets the assumptions, a t-test or something else, depending on what we're doing. We'd set our alpha, which is kind of a decision threshold, and we'd probably use some software to calculate to calculate a test statistic and work out where that test statistic fits on some distribution to generate a p-value, and we would look at that and compare our p-value to our alpha. Or we could use some statistical table. Now, that doesn't tell us whether the effect size is large or small, and I suppose we could just look at the effect size to get a sense of that. The effect size question is, well, what is the size of the effect? And I guess more deeply, what does the size of the effect mean in a practical sense for our research? And perhaps even broader, we might even want to try and quantify the uncertainty around our estimate of that effect. So we need to determine what is an appropriate effect size for our research question. If we're looking at differences between group means, then we might want to rely on something like a Cohens D or an unstandardized group mean difference. Or if we're looking at the relation between two continuous variables, then a correlation coefficient or R squared might be more appropriate. The point is there are often choices there about what effect size is most informative, most meaningful. And we would then interpret the effect size to use using our clinical professional judgment to say what it means. So we could compare it to similar studies in our research area, or we could look at what's typical or use rules of thumb, and so on. So that's the distinction between effect size and significance testing. Now, I already said that, well, if big effects, for a given sample size, the bigger effect, we should have more power, and in general, we should more likely to see significant results, but we shouldn't conflate the two. Another way of, thinking, if our aim is to quantify population effect size, but our sample effect size is an imperfect estimate of that population effect size, we may want to quantify our uncertainty in some way. Now, in a Bayesian framework, we're allowed to make statements like, well, the probability of these effect size being between given values is this. In a frequentist framework, we have confidence intervals, which many people interpret in the same way, and there's a lot of debates about then the value of confidence intervals and when they correspond to Bayesian intervals. But essentially, confidence intervals are trying to give us a sense of the uncertainty around our estimation of some number, some population parameter. And commonly, if we have 95% confidence intervals, and we can have any percent confidence intervals, just 95% is common, corresponds roughly to our 0.05 convention for alpha. We can say if we have a point estimate of our effect size, but we can also talk about our 95% confidence of what that population parameter is. It lies in a specified interval. So the interpretation of this is that if we were to repeatedly sample our from the data generating process, 95% of confidence intervals generated would contain the population parameter. That's kind of interesting phrasing, because I guess what we're saying here is that if we believe that there is a true value to the population parameter, then in truth, our confidence interval either does contain or it does not contain the population parameter. But we sort of want to flip around and think about it in terms of, well, over repeated samples, what's the probability that our confidence interval contains that true value? So, in theory, we can get confidence intervals for any standardized or unstandardized effect size measure, and statisticians often will evaluate the degree to which the interval is accurate in different contexts. But sometimes it can be quite tricky to actually to get that interval in standard software. Often you have to rely on macros and or bootstrapping or some procedure like that. The main point is that confidence intervals around effect size get you thinking about the right kinds of ideas. It forces you to think about the uncertainty in your estimates. It focuses you on population parameter estimation, and it encourages something which we might call meta-analytic thinking. The aim is to start thinking about effect sizes in the population and starting to quantify our uncertainty. And before going on to that in a deeper way, I think it's worth flagging the role of meta-analysis here. Right? The way that meta-analysis is encouraging us to think more about the underlying relationship and not just seeing studies in isolation, to start thinking about what our study says and contributes to an overall understanding of an effect. So, a bit of a diversion, but let's talk about meta-analysis. Meta-analysis is a tool for taking summary statistics, summary effect sizes from published studies and formulating an analysis, an overall assessment of those summary statistics. In particular, so for example, if we were looking at group means, say you were interested in the effect of a particular training program versus no training, we could estimate that Cohens D, or a size of group mean differences in a study. And we could try from, if we had a series of studies, 10, 20, 50, 100, we could start to get an estimate of the average effect across those studies, and we might label that our estimate of the true average effect that's underlying these studies. Alternatively, we might either by theory or by examining the data see that actually these studies are being generated from different data generating processes, which is to some extent surely almost all studies are. Then we might want to start to quantify the degree to which the variation in effect sizes observed is due to true variation in the underlying parameter and what's just due to random sampling. So what I just described there, where there is some true variation in the effects for each study, that's what's known as a random effects meta-analysis. It says that the variation between study effect sizes is not just due to random sampling, it's due to some underlying variation in effect sizes across studies. And that idea often makes sense. If you think about some training programs, might be implemented better or worse, or they might have different samples of people that where, say one sample's better able to learn or has more to learn and so on. There could be all sorts of reasons why the effect sizes could vary. You might have more reliable dependent variables, you might just have better trainers, more money, more resources, who knows. The point is, when we're doing research, often our aim is that we're trying to say something about what's truly going on in the population. We're trying to develop some general theory, and we can use existing studies to provide estimates of effects, and we can contextualize our current research in that framework. And so one of the challenges of meta-analysis is often that dependent variables are on different scales, so we often fall back to standardized measures of effect, such as Cohens D or the correlation coefficient. When we're doing this process, of course, we have to do a range of things. Often there's corrections for variation in reliability of independent variables. There's often weighting procedures to weight studies with greater sample sizes. There's often issues about studies that have been unpublished, Bayes draw effects as they're often known. So these are all part of the meta-analytic process to try and get a more true estimate of a given population effect. In addition, with meta-analysis, if you have enough studies and you're able to code those studies for various properties, you can start to see whether characteristics of the studies are actually influencing the effect size. So you might say you have this variation in effect sizes, which is captured in the idea of a random effects meta-analysis, but you may then be able to start explaining that variation by saying, training studies with participants who had more to learn were showing greater increases, greater effect sizes than those where you're teaching people who, say, already know the material pretty well. So this has implications for when you're doing a literature review, that often you can focus on meta-analyses that provide a good quantitative summary of existing research, but it also provides a framework for thinking about your own results, contextualizing it, providing a sort of expectation about what's already out there and seeing not your study in isolation, but contextualized within a broader framework. So Thompson describes this as thinking meta-analytically, essentially reading the existing literature for specific studies for effect sizes, and then contextualizing your own study in that context. So, say for example, you did a study looking at the favorability of tailored messages. I think that's what this meta-analysis was on. And I think we've got Cohens D on the x-axis. What we have in this this plot is every study that's reported an effect size, and it's correlation. But every study that's reported an effect size, and we get an estimate of the correlation in each study. We also get which is by the horizontal line, and we also get, a vertical line. The horizontal line quantifies our confidence interval for that effect in a given study. So studies with big sample sizes have quite short confidence intervals. Studies with small sample sizes would have very large confidence intervals around their estimate. So such a plot highlights the variation across studies. You can start to get a sense of what's typical. We're seeing a lot of studies with correlations in the sort of 0.1, 0.2 range. Most are on the right side of the zero line. There's one or two outliers on the left side. and so on. And meta-analysis would provide more quantitative tools for describing that variation and the mean and the degree to which the model is consistent with, say, fixed effects or random effects meta-analysis. We could start to even look at, if these studies were coded, we could start to look at means and so on. I mean, if you're interested in doing meta-analysis, the metaphor package in R is quite a nice open source option for doing that. The point is, if you were coming along and doing your own study here at the very end of this, you might want to think, well, look, I shouldn't interpret it in isolation. This provides a background for interpreting my effect. So meta-analytic thinking is about designing your study, prospective formulation is about designing your study with the prior effect sizes in mind. A lot of power analysis tools and sample size determination will ask you to enter an effect size. So by thinking meta-analytically, you can take existing research to get a sense of what kind of effects you would expect and therefore work out what sample sizes you might need. The other thing is the retrospective interpretation of your results by comparing your effects to existing research. Now, I label this a form of naive Bayesian reasoning. Not necessarily naive in a bad sense. It's just that it's a kind of a qualitative way of comparing quantitative information. It's not an integrated statistical framework like Bayesian statistics, but it's a way of contextualizing and interpreting your results or your effects in a broader context. And if you're more interested, then you could explore Bayesian statistics, which provides a quantitative, systematic framework for incorporating your prior understanding into interpretation of subsequent results. I should also flag, just at this point, I think it's worth also encouraging you, and it's a bit of a diversion, but to encourage you to consider data sharing and replication. This is a big issue at the moment for the scientific community. And yeah, it'd be really great to see more people sharing their raw data in scientific contexts. Nature's got a new journal devoted to sharing data. A lot of journals have online supplements. There's repositories like Figshare or university repositories for uploading data and providing that data in an accessible form with good metadata and so on. And this really is helpful for more sophisticated meta-analysis, allows for greater scrutiny of analyses, which can be challenging. But yeah, I think in terms of moving science forward in psychology, if there was greater data sharing, we could. So let's talk about power analysis. Power refers to the probability of correctly rejecting the null hypothesis when the null hypothesis is false. Thus, we can arrange the possible outcomes of an experiment in a 2x2 grid, where we distinguish between, on the one hand, the objective status of the null hypothesis, whether it is true or false, and on the other, the decision, whether we retain the null hypothesis, whether we reject the null hypothesis. This creates 4 cells. Now, if we have these 4 cells, some of these are particularly important such that we give them labels. So if the null hypothesis is true and we reject the null hypothesis, we've made a mistake, haven't we? We've said that there is an effect when there is no effect. And this is obviously very bad if it was concluding that the drug was effective when it was not, that a lot of money could be spent on that drug unnecessarily, or unnecessarily giving people hope. So we refer to that as a type 1 error, perhaps type 1 because it's in some sense seen as the most important error. And alpha controls that type 1 error rate to a particular level. So we specify alpha to control that error rate, if the null hypothesis were true. If the null hypothesis is false, we can either correctly reject the null hypothesis, and that the probability of doing that is our power. Or we can make what's called a type 2 error, where we retain the null hypothesis, even though it is false. The probability of doing that is often labeled beta. Now, that's a particularly undesirable thing to do as well, but we don't specifically control that. Rather, it's influences by things like sample size and alpha and the population effect size. So if we want to increase our power, which I argue is generally a very good thing to do, because what's the point of doing research if you don't have a reasonable chance of finding the effect that is there, assuming it is there. Well, we can increase our effect size, we can increase our sample size, or we can increase alpha. But it's worth thinking about what each of those things mean and whether they're something we want to do. Increasing effect size is an interesting idea. This can be manipulated in a number of ways by manipulating our experiment. So we can increase effect size in an experiment by increasing the dosage or having more contrasting groups. In a correlational design, we might want to increase the reliability of measurement of our dependent variable, averaging over more sessions, more trials, more items. All these things have the potential to increase our effect size. And whether that's, sometimes we're not interested. Sometimes by changing the effect size, we're changing the thing that we're actually studying. So that can be an undesirable thing. Other times, that's quite reasonable. And that's fine. We can also increase our sample size. So that's certainly a good thing. And thinking about how to maximize your sample size when you do your thesis or any study is a really important thing to do. Thinking about pragmatic ways to increase your sample size. Because greater sample size means more power and more precision in estimating your parameters of interest. Increasing alpha is probably not something you generally want to do. Often it won't even be acceptable to your readers to alter your alpha from, say, 0.05 to 0.1 to 0.2. The main, implication of alpha really is to think about the implications of having more focused analyses rather than data dredging. Because effectively, if you're doing a lot of significance tests, then the chance of one being significant will, if none were true in the population, it increases. So effectively, some may argue that you should be correcting your alpha for the number of tests you're running. So in some senses, whether you do that or not, people may be doing that in their heads when they read your research. So in some senses, reducing the number of analyses or presenting your analyses in a parsimonious way is sort of a way of keeping your alpha, assuming you're sort of either explicitly or implicitly doing an alpha correction on analyses. Another really important point is that power is a property of a hypothesis, not a study. I don't know how many times I have met people talk about, I want to have reasonable power for my study. Power is not a property of a study, it's a property of an hypothesis. Think about that. Your study may be investigating many effect sizes and testing several different hypotheses. For example, if you're comparing two groups, treatment and control, on several dependent variables, each of those dependent variables is an hypothesis, whether there's group differences, and each will presumably have a different population effect size, and therefore each will have its own statistical power. Even if alpha and sample size is kept constant, effect size may vary, and typically will. So, in many studies, actually, I guess people are interested in a wide range of hypotheses, and you'll find that some you'll have massive power and some you'll have very small power. A classic example is people who study moderation effects and multiple regression analyses. They've got several predictors. They're also interested in some interactions between those variables. They're also interested in the overall R square of their model. Very common for the overall R square to be a very large effect, very high power. Even some of the individual coefficients, strong relationships like neuroticism with well-being might be very large effects. But when you get into the interaction effects, they might be tiny. Very small interactions between, say, two personality variables on stress or something. The power of that moderator hypothesis might be very small. And so when you're designing your sample size, you want to take that into consideration to justify the sample size you have in terms of effect sizes of interest. You may have to have the trade-off of having sufficient sample size for some effects, but not others. Okay, so assuming you're doing designing a study or assessing your study, you want to be able to answer certain questions like, what sample size do I need for a given power, assuming I know effect sizes and so on, or what power did my study have? Now, to do that, a really great tool, and there are many tools out there, is gpower3. It's a GUI for doing power analysis. It's free, and it provides a priori and a post hoc and other forms of power analysis for most of the most common statistical tests that you might be running in psychology. So by a priori power analysis, I mean you're trying to determine the sample size you need. A priori, you know the effect size and so on. You want to work out what sample size you need. Or post hoc, you try and work out what power you did have for a given study. It's also a good way to learn about power analysis, learn about rules of thumb, and see how sample size, effect size, and so on is organised. So what we have here is a few examples of looking at power analysis. This first slide shows three studies looking at three groups where we have some population means and a population standard deviation. It's looking at differences in intelligence between three groups, and the question is, what is our statistical power given different configurations? And so in the first example, we have a certain effect size, F, which is defined by the differences between group means relative to the standard deviation, with a total sample size of 60, alpha at 0.05, and we see that we have 43% power. Alternatively, if we increase the differences between the group means, 120, 100, 110, our effect size F is about doubled, we now have 96% power, so quite an increase. Or down here, we see we've kept the effect size the same, but we've halved the sample size from the second example, and now we only have 0.71, 71% power. So you can see, by playing around with this, you can explore the statistical power of your study. This graph here on the left, we have a red line and a blue line, and the red line is the distribution of the test statistic, F in this case, when the null hypothesis is true, and the blue line is the distribution of the test statistic where the null hypothesis is false. The green line indicates critical F, i.e. results where when F is larger than that, we reject the null hypothesis. And in this first example, we see that the blue line is substantially on the left of that critical F. So a lot of the time, we're going to be getting F values that are less than critical F. So we're not concluding that the actual effect that is there, we're not finding it. In contrast, you can see with the ladder plots, that blue distribution goes much more to the right of critical F, meaning it's a graphical representations of the probability of rejecting the null hypothesis. So here's just some more examples which you can explore. Exploring changes in alpha and so on. So a priori power analysis, takes an effect size, an alpha, and power to determine what sample size you need to do a power analysis. Post hoc power analysis says, well, given my sample size, effect size, and alpha, what was my power? We can also explore curves of relationships between different variables to get an intuition. So here's 4 different population correlations with sample size on the x-axis, and we can start to see the statistical power we have for detecting a significant correlation. So with a 0.2 correlation, we're getting up to sample sizes almost around 200 before we're getting a significant 0.8 power. Whereas if we think our correlation is more like 0.4, well then we only need a little under 50 to get 0.8 power. So really it's just highlighting the importance of thinking about your correlation that you're trying to estimate, or the effect size, and seeing the relationship there with power. One other thing I wanted to talk about is this idea of accuracy in parameter estimation. That the power analysis is not always what we're concerned about. Often we're not concerned so much with the null hypothesis, particularly in psychology, where it's more about getting an estimate of whether an effect is large or medium or small. A lot of selection and recruitment research focuses on the importance of correlations between predictors and job performance. And so, it's known in the literature that personality predicts job performance and that intelligence predicts job performance. But in general, the correlation between intelligence and job performance is much larger than the personality one. So if you were making recommendations about what test to use, you'd say, go with the intelligence test, all else being equal. And the point here is that it's not just whether that correlation is significant from 0. You want to get an estimate of that size of that effect. And so is the case with a lot of psychological research. It's about getting a precise estimate of the size of the effect. And so accuracy in parameter estimation is just a framework for getting you thinking about the importance of ensuring that you get small enough confidence intervals to make the inferences you want, able to answer questions about what sample size is required in order to get sufficient confidence intervals. So in that case, even if you've got enough power with a given sample size, you may still want more people to not just rule out 0 as an explanation, but to even get more precision in your estimates. So the basic advice from all this is, sample as many people as you can, and be aware that there's often fairly large confidence intervals around published results, and that it takes quite large sample sizes or many different studies to really fine-tune precise estimates of effect. I guess I'm also trying to say that you shouldn't replace a blind use of p-values with a blind use of effect size or power analysis. Where blind use of effect sizes is just not thinking about what effect size is the most relevant to your data, or just glibly using one of Cohen's rules of thumb without really thinking about what this effect means in your research context. And power analysis fundamentalism is just assuming that, a study has a power rather than an effect has a power, assuming that we know what the effect size is when it's actually sort of a little bit uncertain. Or assuming that power is what you want when maybe you're more concerned with accuracy and parameter estimation. I guess I'm trying to say that you should see results in terms of a meta-analytic context, in terms of where your study's result fits into a broader quantitative framework of existing effect sizes. And that, sample estimation is more than just power analysis. There's a lot of constraints that go into working out what is an appropriate sample size in terms of resource allocation, efficiency of getting participants, the trade-offs of more or less power, and so on. So that finishes me up for today, and I'll thank you for listening.